So in the last lecture we studied equations like this: y equals x to the 10, which is a power law, and we found out, for example, how we can differentiate that and how we can integrate it. And in this lecture we're going to look at functions like this: y equals 10 to the x. This is an exponential function because x is in the exponent. So not x to the 10, but 10 to the x. Now, exponential functions increase a lot more quickly than power laws. And to illustrate that, I've put up this table where we've got x down here, and then x to the power of 10, that's the power law, and then 10 to the x, that's the exponential. So when x is 2, x to the 10 is 1024, and 10 to the x is 10 squared, which is 100. So at this point, x to the 10, the power law seems to be winning. And when we go to x equals 3, the 3 to the power of 10 is 59,049, which I can write in the standard form as 5.9 times 10 to the power of 4. And 10 to the x is 10 to the power of 3, which is 1,000. So the power law is still winning at this point. And then when we go to x equals 4, we get this is a million and something, so that's roughly 1.0 times 10 to the 6, and this is 10 to the power of 4. And then at 5, we've got, for x to the 10 is 9.8 times 10 to the 6. This is 10 to the 5. So still the power law is winning. As we get down to when x is 10. Well, when x is 10, this is just 10 to the 10. So I've just written that as 10 to the 10. And also, so is 10 to the power of x, because it's now 10 to the power of 10. So at this point, the power law and the exponential are equal. So the exponential has now caught up with the power law. And then as we go further, now the exponential is definitely winning. So this is now down at 2.5 times 10 to the 10 compared to 10 to the 11. And this is 6.2 times 10 to the 10 compared to 10 to the 12. And as we, if we continue on beyond here, the exponential will completely swamp the power law. So if we plotted a chart of x, the power law would look something like that. Should be going up smoothly. And the exponential would seem to be lagging behind, but then at a certain point it crosses over and it goes up massively, while the power law is just still sort of trundling along behind. So let me just label those to be completely clear. So that's 10 to the x, the exponential, and that is x to the 10, the power law. So, as I say, the exponential function increases much more rapidly than a power law. And that's when the index is positive. If we took the reciprocals of this, so this would be 10 to the minus x, taking the reciprocal, then an exponential function decays much more rapidly. So because these numbers are getting bigger, when we take 10 to the minus x, that's 1 over them, these numbers get smaller and much more quickly than with the power law. So that if we're looking at things that decay according to an exponential, they will decay very rapidly. So at first, it might be slow like this, but then at this point, those numbers are hugely increasing. So when we take in the reciprocal, they're massively decreasing. Whereas the power law might be below it here, but it will decay more slowly because those numbers are increasing more slowly here. Then if we take in the reciprocal, they will decrease more slowly. And this is important because in, for example, the financial markets, many models used by financial analysts to calculate risk assumed that the probability of large fluctuations in stock prices and in the value of financial instruments would be depend on an exponential function, a decreasing exponential function, so that the probability of very large swings would be very low because they assumed it obeyed an exponential law. But in fact, evidence suggests that it really obeys a power law. So the chances of very large events are actually much higher than were calculated with models that assumed this exponential decay. And so risks were much greater than estimated, and it meant that you could have much bigger crashes, for example, than people expected. And we say that a power law has a long tail. I should perhaps again put that. This is the power law, and that's the exponential, decreasing exponential with a negative exponent so that the numbers get smaller. We say it has a long tail. The exponential drops to a negligible value, practically zero, very quickly compared to the power law, which takes a much longer time to get down to something negligible. And we'll be talking about that in more detail later on. And power laws are an important function that we find in socio-historical processes. But exponentials are also important, and that's what this lecture is going to continue on with. Okay, I've put up here two functions. One is linear and the other is exponential. So the linear one is y equals 10x. We know this is linear because it just depends on x, x to the power of 1, as we discussed in the last lecture. And the exponential one is the one we've just been looking at, y equals 10 to the power of x, so x is in the exponent. And here we've got x, so it's 0 up to 6. And I've put in the values for y equals 10x. The linear function is just 0, 10, 20, 30, etc. So up to 10 times 6, which is 60. And then for the exponential one, done the same. So when x is 0, 10 to the power of 0 is 1. We may remember from the laws of exponents, 10 to the power of 1 is just 10, 10 squared is 100, and so on. So these are just the powers of 10. So, you know, both functions pretty straightforward. And what we notice is that in the linear one, as x goes up in equal steps, so it's going up by 1, adding 1 at each step, this also goes up in equal steps. We just add 10 at each step. But with the exponential function, that's not the case. We're not adding the same amount at each step. We're multiplying by the same amount at each step. So this goes up in equal ratios. The x is going up in equal steps, but the exponential function is going up in equal ratios. And another term that's sometimes used is for a series of numbers that go up in equal steps is an arithmetic series. So this function is arithmetic. And for something that goes up in equal multiples, equal ratios, it's said to be a geometric series. So this exponential function, we could also say, is geometric. And if we find in our historical models that we've got two variables related by an exponential relationship, it means that as one of the variables goes up in equal steps, the other goes up in equal ratios, equal multiples. And so the question will be, well, why is that? Why is it that as one variable goes up in steps, the other goes up in ratios? And an example of that in real life is Moore's law of semiconductors, which says that the number of transistors that can be fitted on a computer chip doubles every 2 years. So Moore's law would look like this. Here's the time in years, so 0, 2, 4, 6, 8, 10 every 2 years. And here's the number of transistors on a computer chip. Well, I've started it at 1 just for illustration. So it's going to double. So 1, 2, 4, 8, 16, 32. That is a geometric progression because it's doubling. It's going up by a factor of 2 at each stage. Well, this is arithmetic. We're just adding 2 years at each stage. And so with Moore's law, the question is then, why is it that as time increases in equal steps, the number of transistors on a chip goes up by equal multiples, not equal steps? And as we go through this lecture, we'll come back to that question and see how we can move towards answering such a thing once we have some better understanding of where exponentials come from. And I should say that Moore's law is now breaking down, or has broken down, as semiconductor technology comes up against physical limits. But computing is moving towards other technologies like quantum computing, so it's not necessarily relevant anymore. And now we'll just look briefly at the idea of a logarithm. So if we have y equals 10 to the x, we've called this the exponent. We've also called it the index, and we've also called it the power. And now we're going to introduce another name for it, which is the logarithm. So if y equals 10 to the x, we say x is the logarithm of y. X equals the log of y. And we specifically say it's the logarithm to base 10 in this case, because we could have, say, y equals 2 to the x, and in that case x would be the logarithm to the base 2 of y. And we can see here with these numbers then, the logarithm to the base 10 of 1 is 0, the logarithm to base 10 of 10 is 1, the logarithm to base 10 of 100 is 2, the log to base 10 of 1,000 is 3, and then 4, and so on. But we can have logarithms for arbitrary numbers. So, the logarithm to base 10 of, say, 2025 would be somewhere between 3 and 4. And I've written it down. It's is about 3.3. So in other words, 2025 is 10 to the power of 3.3. Now we're going to look at a useful thing for studying exponentials through graphs, which is a semi-logarithmic plot. So firstly, let's consider plotting this exponential function here on a graph. So I'm going to put x along the bottom and y up here. So going from 0, 1, 2, 3, 4, 5 up to 6. And when x is 6, y is 1,000,000. So we want to go up at least as high as 1,000,000. So I'll put y, measure that in millions. Going up as high as 1,000,000, and we start at 0 here. So we can go 0.2, 0.4, 0.6, 0.8 millions. So we're easiest if we start up here at 6. So when x is 6, y is 1 million. So we're somewhere up there. And then when x is 5, y is 100,000. So that's 0.1 million. So when x is 5, we're down here. And then when x is 4, we're at 10,000. Well, that was a tenth of that. So 10,000 is a tenth of that. So I probably put it too high there. And then 3 is, when x is 3, it's a tenth, and so on. So these are just, merging with the x-axis. So our exponential function on that graph looks something like that. As you can see, it's how it's increasing very, very rapidly at this, and so this completely swamps the earlier values. So what we can do though is plot it on a semi-logarithmic plot. So we've again got x 1, 2, 3, 4, 5, 6. But for y, we don't go up in equal steps, we'll go up in equal ratios on this axis. So I'll put that in. Okay, so now we've got a scale that goes up in equal ratios, and this is a logarithmic scale, we say. We'll see in a moment the reason why it might be called a logarithmic scale. But so this is a logarithmic axis, and now if we plot our points, we're at 0, it's 1, at 1 it's 10, at 2 it's 100, and you can see it's going to go up. Yeah, 5, 6. So it's, in other words, just a straight line. And this is called a semi-logarithmic plot. And if we plot some data on a semi-logarithmic plot and we get a straight line, then we know we're dealing with an exponential relationship.
We can also see more detail of what's happening for the small values.
Now I said here that we have marked our scale in equal multiples rather than in equal steps. But another way of thinking about it is we could say this is what we're plotting is the logarithm of y up here. So this is 0, 1, 2, 3, 4, 5, and 6 is the logarithm of y. So instead of having special graph paper with a logarithmic scale, we just plot on ordinary graph paper the logarithm of y against x. Hence the term a semi-logarithmic plot. Okay, now we'll talk about the derivative of an exponential function. So we've got y equals 10 to the x, and the question is, what is dy by dx? Well, deriving from first principles the derivative of an exponential function is pretty technical, and I'm not going to go through it, and particularly because the proofs of it tend to be somewhat circular in my view. But what we can do is accept it as an empirical fact that when we find the derivative of 10 to the x, it is a constant times 10 to the x, constant k times 10 to the x. We can verify that empirically by just plotting the graph of 10 to the x and measuring the slope, and we will find that the slope at every point is a constant of the value of the function at that point, 10 to the x. And we can do the same for, say, y equals 2 to the x. and we find that dy by dx equals a constant times 2 to the x. Now, to distinguish these, I'll put, because this is a different constant, so I'll call that k2 and we'll call that k10. And then if y equals 3 to the x, dy by dx equals k3 times 3 to the x. And what we find, the values of these constants, k10 is k10 is about 10.3, k2 is about 0.7, and k3 is 1.1. And in general, for any value a, if y equals a to the x, dy by dx equals ka times a to the x, where k is some constant. And when we look at these values, k10, k2 and k3, we can see that the larger a, the larger the constant. So when it's 2, it's 0.7, when it's 3, it's gone up to 1.1, and when it's 10, it's gone up to 2.3. And we'd find that the larger the value, the larger the base of the exponent, the larger this value k when we find the derivative. And what that tells us is that somewhere between 2 and 3 there will be a k that equals precisely 1. So for some value of a between 2 and 3, the constant when we differentiate it is exactly 1. And we call that value of a e. So if y equals e to the x, then dy by dx equals the constant times e to the x, and this constant is 1. That is our definition of e, and it comes out as e is about 2.7183. Okay, so we have this thing y equals e to the x, and then this is really the definition of e. It's the value where when we differentiate this we just get back the same thing, e to the x. And we know from the idea of logarithms then that if y equals e to the x, x equals the log to the base e of y. That's just the definition of it. But we often write, instead of log e, ln, the natural logarithm. So this is known as the natural logarithm of y. So when we have the base e, it's called the natural logarithm. Okay, now we've seen that we've got y equals e to the x. So dy by dx is equal to e to the x. And interestingly, since y equals e to the x, dy by dx equals y. Now what if we have y equals a e to the x, where a is some constant? Well, when we differentiate this, because a is a constant, that doesn't change, so we can kind of slide past it and differentiate e to the x. but when we differentiate e to the x, we just get e to the x. So dy by dx equals a e to the x. And again, that's just equal to y. So when y equals a e to the x, differentiating it still gives back the original thing. What if y equals e to the kx? Well, to differentiate this, we can use the chain rule. Let's just remember what that is, which is dy by dx is equal to dy by dz times dz by dx. So if we call this e to the z, then dy by dx equals, I'll put it up here first, dy by dz times dz by dx. Well, dy by dz, if y equals e to the z, dy by dz is just e to the z by what we already know. And dz by dx, well, if we say that z equals kx, which is what we've just been saying, well, we should remember from the last lecture, differentiating dz by dx is just k. As the rules of differentiation that we considered in the last lecture. So we can put that in here. And then you can just replace z with kx. And lastly, just to make this a bit neater, we'll just swap those round. So it's k times e to the kx. So if y equals e to the kx, dy by dx equals k times e to the kx. So we think of it as we bring the k down in front. And we use the chain rule for that. And this chain rule is very useful in situations like that, where we've got to differentiate something that isn't immediately like something we know. We know that y equals e to the x gives dy by dx equals e to the x. We haven't got a rule for e to the kx. We can use the chain rule as we've just done. And the way we tend to think of it is that we say we differentiate the thing, differentiate the bracket. So we treat the complex thing, in this case kx, which I've said is the bracket because it often is a bracket, though it isn't in this case, but you know, we could put that in brackets. But we differentiate it as though the bracket is itself, the thing in the bracket is itself a variable. So differentiating e to the kx, if that's just the variable, we'll just get e to the kx. But we then multiply by the differential of the bracket, we say, and the differential of kx is k. So that's how we get our k e to the kx. So we don't necessarily need to write out the chain rule explicitly. Once we've got some practice, we can just do this kind of thing in our head. We, treating that as a variable and finding the differential, and then we differentiate that and multiply by it. So y equals e to the kx gives us dy by dx equals ke to the kx. So in this case, we get dy by dx equals ky. And we'll often see these situations as you know, as we go through into the socio-historical processes, that a rate of change of something is a constant times itself, a constant multiple of itself, and that then tells us that it is an exponential function e to the kx, where k is whatever that constant is. And just to finish off, what if we've got y equals a e to the kx, which is the most general form? Then dy by dx is going to equal, well, again, the a is constant, so we can kind of slide past it, and we're going to get a k e to the kx. So it becomes ak or k8 e to the kx, whichever way around you like to put it. So in other words, this is again just k times y. As we've got a e to the kx, and we've just got an extra k, so it's k times y. So I said that if we see dy by dx is a constant multiple of y, we know that it is an exponential function of the form e to the kx. But actually, it's more general. Could be some constant a in front of it. And this really corresponds to a constant of integration, because we're starting here with telling you what the derivative is. So when we're trying to go back to find out what y is, we're integrating, and we've got a constant of integration, and that's this constant a. In a little bit later in this lecture, we'll clarify that a bit more, how that's related to the constant of integration. Okay, now before we were considering something like y equals 10 to the x. Now we know that if 10 equals e to the z, let's say, then z is the logarithm of 10. That's the definition of the logarithm. Z equals log 10. These two things imply each other. As I say, that's just purely a definition. So in other words, 10 equals e to the log of 10. So raising something e to the power of something, or we might say taking the exponential of something and taking the logarithm of it, they're kind of opposites. They cancel each other out. So if it's 10, we take the logarithm, and then we take e to the power of that, we just get back to the original thing. So they undo each other. They're kind of inverses of each other. So anyway, we can use this fact then that 10 equals e to the log 10 to write that y here equals e to the log 10 to the x. And then we can use our exponent rules to rewrite that as e to the log 10 times x. So now we can differentiate, and let's just remind ourselves that if y equals e to the kx, dy by dx equals k e to the kx. So here k is log 10. So dy by dx is equal to log 10 times e to the log 10x. And we can write that as log 10 times e to the log 10 of x is the same as 10 to the x from here. So that is, we can turn that back into 10 to the x. So dy by dx, if y equals 10 to the x, dy by dx is log 10 times 10 to the x. And if you remember earlier, I said that when y equals 10 to the x, dy by dx equals some constant, which I just wrote as k10 times 10 to the x. So now we see that that constant k10 is just log 10. So and if it were y equals 2 to the x, dy by dx would be k2 times 2 to the x. k2 would be log 2. So that's not necessarily something very important, but it's just tying up a loose end when I talked about those constants. In fact, I said that's not very important, but this idea that we can turn something like 10 to the x into e to the log 10 times x. In fact, that is something that we will be using later on in some of the historical theories. We will be transforming some equations using this kind of principle. So yes, it is something to note. And let's now think a bit more about in terms of differential equations. So suppose we're told that the rate of change of a certain variable is proportional to the existing value of the variable. So in other words, dy by dx is proportional to y. Or in other words, we can write dy by dx equals ky, which we then know means that y equals ae to the kx. And supposing we're told that when x is 0, the initial value of y is y0. Then we can put that into this expression here. We get that y0 equals a e to the k times 0, which is, this is k times 0 is 0, e to the 0 is 1, it's just a. So y0 equals a, or in other words, a is y0. So if we've got an expression like this, dy by dx equals ky, it means that y equals y0 e to the kx, where y0 is the initial value. Now, something that behaves like this, that the rate of change of the variable is proportional to the existing value of the variable, is human population growth. There is a certain birth rate. It's so many babies per 100 people. And there's also a certain death rate. It's so many people per 100 who die each year. So the net growth rate is a difference between these two, and it will also be so many people added to the population per year, the difference between the births and the deaths.
The point being that the net growth rate is a given fraction of the existing population.
So we can write that using p for population, the rate of change of population dp by dt equals some fraction, which we usually write as r, of the existing population. So it might be 1%. So r might be 0.01, for example. But the key thing is that the population growth rate is proportional to the population. And so that tells us that the population is going to be equal to p0 times e to the rt. p0 being the initial population at time 0. So population growth is exponential because the population growth rate is dependent on the existing population. It's proportional to the existing population.
The hyperbolic growth of world population is another issue to be dealt with later.
And this is what worried Thomas Malthus, the 18th, 19th century clergyman who wrote about human population growth. He said that population growth is exponential. So it's going to look like that. Whereas he said that the ability to feed people, our technology, as it's against time, that's population, our ability to feed people, our technology, increases linearly. So if we do technology on here, it's just going up steadily, he argued. I'll put T for that. technology ability to feed people. And he used the terms geometric and arithmetic. So he said population growth is geometric, which we saw is another way of saying exponential, whereas the growth of our technology, our capacity to feed people, is only arithmetic. And what that means is that the population is going to tend to go beyond what we can support. Well, that can't actually happen, but population will just increase, because if it goes beyond it, then people will die. But population can't increase beyond it, but because it can increase so much faster, it will always be bumping up against this limit of technology. And he said that that means that people will always be living in absolute poverty. They'll be living at the absolute margin beyond which, if they were any worse off, they would start to die. But they'll be, so the human population growth ensures that the population of the world, or most of it, is living in the direst poverty imaginable. That's what worried him. And this is known as the Malthusian trap, the ability of population always to increase to what is the maximum that can be supported, ensuring that there's only just enough to go round for everybody, and therefore the average person only has just enough to survive. And we'll be talking about that, the Malthusian ideas and their implications and how valid they are, in the module on social evolution and progress, when we'll get to grips with population growth through history. And then another example where this kind of thing applies is with Moore's law. So with Moore's law, we've discussed it. It says that the number of transistors on a computer chip, which I'll write as n, is proportional to 2 to the half t, because it doubles every 2 years. So if we're measuring t in years, after 2 years this will be 1, after 4 years this will be 2, so it's going 2 to the 1, 2 squared, and then after 6 years it will be 3, so it'll be 2 cubed. So it's doubling every 2 years, so that is 2 to the half t. And it will start at some initial value n0. So Moore's law is an expression of that kind. A is n0. And we've got 2 to the half t, but to put it in terms of e, remember that 2 is equal to e to the log 2. E to the power of and log are inverses of each other. So this is n0 times e to the half log 2 times t. So just to put it in that form with e rather than 2. And so we know with an equation like this, if y equals ae to the kx, then dy by dx equals ky. So in other words, Moore's law says that dn by dt equals, and it's a half log 2 times n. K is a half log 2 in this case. It doesn't really matter the precise value for our point now. Yeah, okay, let's leave it as that, half log 2. So that's what Moore's law is claiming. It's saying that the rate of increase of transistors on a computer chip is proportional to the existing number of transistors that you can fit on a computer chip. And so we're now beginning to sort of be able to frame the Moore's law in a way that we can start to ask the questions about, well, why is that? Why is it that the rate of increase of packing transistors onto a chip should be proportional to the number you've already got on there? And we'll be coming on a little bit later in this lecture to moving a bit closer to be able to answer that. And if you really want sort of bonus points, you can start to say, and why is it half log 2? Why is it this particular value? Then you've completely explained not only the general form of Moore's law of a doubling, an exponential law, but precisely the fact that it's doubling every 2 years. Okay, now let's think about what happens if we have data that obeys this equation, y equals ae to the kx, and we plot it on a semi-logarithmic graph. Before we do that, I just want to go over something to do with logarithms. So let's suppose we have a equals e to the power of a. This is not the same a, this is just an arbitrary a. And b equals e to the b, little b. And we want to find the log of a times b. Well, the log of a times b is the log of e to the a, e to the b. And e to the a times e to the b is e to the a plus b. And the logarithm of e to the a plus b is then just the definition of the logarithm is just a plus b, which is equal to the log of a plus the log of b, because from here, by the definition of the logarithm, a is the log of a and b is the log of b. So the log of a times b is the log of a plus the log of b. It's a very important idea that we need to remember. And we can say then that sort of taking logarithms converts multiplication into addition, the same way as on a semi-logarithmic graph. By using a logarithmic scale, we convert equal multiples into equal steps. Okay, so going back to this then, the reason I've mentioned this is because we're going to use that here. So let's take the logarithms of both sides. So on one side we've got the logarithm of y. That's going to be equal to the logarithm of a times e to the kx is going to be the logarithm of a plus the logarithm of e to the kx. Well, by the definition of the logarithm of e to the kx is just kx. So if we have some data that we think obeys this exponential law, and we plot the logarithm of the y against x, we're going to have a straight line, because this is like the old equation for a straight line, which is mx plus c. So we can see that k is going to be the slope of the line m, and log a is going to be the constant c, the y-intercept. And logarithm of y corresponds to the y, the variable on the vertical axis. So when we plot log y against x, if we've got some data and it does obey an exponential law, it might be, you know, population growth or something, then we should find a straight line. The slope is the k in the law, and this y-intercept is log of a, the value, the constant in front of it. And so if we think about Moore's law, for example, we would see that Moore's law is true if we plotted for x time, let's put that in a different colour. For Moore's law, we'd plot for x on the x-axis time, and on the y-axis we'd plot log of n, the number of transistors on a chip. And then we would find something like this, and we would see a straight line, and that would confirm that Moore's law is true. Because it is an exponential law. So we've seen that when we have an exponential relationship between two variables, it means that as one of them goes up in equal steps, the other goes up in equal ratios. And we're now going to look at something called a Weber-Fechner law. Weber-Fechner, that describes a situation in which that can occur. And so when we look in our historical data and find an exponential relationship between two variables, we can ask ourselves, is this a situation where a Weber-Fechner type of effect might explain it? And what the Weber-Fechner idea is about is that human perception is sensitive to the relative changes in things, not the absolute changes. So a classic example is if you're in a dark room and you switch on your phone, the light from your phone will light up the room. But if you're in a room that's in broad daylight and you switch on your phone, you won't notice any extra light in the room. You won't notice any increase. So the phone adds an extra light, the same amount of extra light in both cases, but in the dark, it's proportionately a much bigger change than when you're in daylight. Or we could think about, having some candles in a room. If you've got one candle in the room and then you add an extra candle with one, you're going to double the amount of light. But if you've got 10 candles in the room, you add an extra candle, you've added 10% to the amount of light that's already there. And if you've got 1,000 candles, you've added only 0.1% extra light. And this would explain why you adding an extra candle, if you've already got 1,000, you're not really going to notice the difference. But with one candle, you are. Here it's a doubling. Here it's 10%. Here it's 0.1%. Our sensitivity to it depends on this fraction, not on the fact that it's one extra candle. You won't notice it if you've already got a large number there. Or you could think about if you're doing a journey of 10 miles and you are asked to make a detour of 1 mile or go 1 mile further, let's say. That will seem quite a big thing. To you're going 10 miles, to go an extra mile is quite a big thing. But if you're going on a journey of 1,000 miles and then you have to go an extra mile, you're not really going to notice it. What we're saying there is that adding an extra mile on a journey of 10 is adding 1/10 to your journey, whereas adding an extra mile on a journey of 1,000 is only adding 1,000th to your journey, and 1/10 is not equal to 1,000th. So we don't perceive these as being the same thing. But if we had a journey of 1,000 miles and we were required to go an extra 100 miles, then that would be the same thing, because that's a tenth, and again a 10%. So adding 100 miles to a 1,000-mile journey feels the same as adding an extra mile to a 10-mile journey. So then we would notice it just as much as we would notice adding a mile to a 10-mile journey. So a Weber-Fechner law basically describes this idea. So if we write down S as the absolute stimulus. So that is one candle, that's the absolute stimulus, and Z as the perceived stimulus. So that's how much we notice the extra candle, which we've been saying we notice it, how much we notice it depends on what's already there. We can then say that ds is the change in the absolute stimulus. So that's one extra candle, let's say. And dz is our perception of the change in our perception. So that can be big or small depending on for one candle, whether the perception can be big or small depending on what we're adding it to. So the change in our perception, the perceived change, is equal to the fraction as to what's already there. So we said that if S is 10 candles already, then and the change is one candle, ds is one candle, that's 1/10, that's 10%. But if S, so the perceived change is going to be 0.1. But if there's 1,000 candles there, ds over S is 0.1% or 0.001. So dz will be a lot smaller. The change in perception is dependent on the stimulus that's already there, and the larger S, the smaller the change in perception. So we can rearrange this. We can put the S up there, that side, and take the dz down to the other side, gives S equals ds by dz, or in other words, just putting it the other way around, ds by dz equals S. And we should recognize that now, that this is like dy by dx equals y, which we know has solutions y equals ae to the kx. So in this case, we're going to have S, because S plays the role of y, and Z plays the role of x. So we're going to have S equal to, well, let's just put it here as proportional to e to the k z. And then if we take logarithms of that, log s, and the logarithm of e to the kz is just kz. So the logarithm of the s is proportional to kz. Well, k is just a constant, so saying it's proportional to the constant times z is just saying it's proportional to z. So that tells us that z is proportional to log s. So in other words, the perceived stimulus is proportional to the logarithm of the absolute stimulus. The absolute stimulus is the number of candles that we have, and the perception is of how much extra light that feels like.
So if z is proportional to the logarithm of s, s is proportional to e to the z, implying an exponential law.
And another way we could write this is this law, the Weber-Fechner law, dz equals ds over s. We could also write it that 1 over s ds by dz is a constant. If you rearrange that, which is is just sometimes another way of recognizing it. It's saying that ds by dz is the proportional rate of increase in the stimulus with respect to z. So it becomes a percentage rate of increase with z. And it just leads to the same thing. It's just another way of writing this equation here. It's taking the s down to the other side. So let's write that up again. We're saying that the perceived change in the stimulus is proportional to the relative change of the absolute stimulus, and then that implies that our perception is proportional to the logarithm of the absolute stimulus. And a possible example of that is in human life, that life itself is logarithmic, so that when we're 10 and we age to become 11, that's an extra year of life experience, and that's an extra 10% of life experience. And perhaps when we're 20, we have to go, well, when we're 20, we have to go 2 years to 22 to get an extra 10% of life experience. And perhaps that feels the same to us. It's the relative increase in our life experience that is what we perceive as our aging. And so when we're 50, it has to be an extra 5 years to feel the same amount of growth as from 10 to 11. And so we would then say, if we write our perceived change of life experience,
using the Greek letter tau to represent perceived time,
it's proportional to the fraction of our life so far, measured in the calendar years, actual time. So we've got, again, a Weber-Fechner law, and that means that our perceived age, our perception of the time that we've been around, is proportional to the logarithm of the calendar time. And so as calendar time increases, we have to go that many more years to get the same increase in perceived time. That's why, as I say, life feels logarithmic. It feels as though it's speeding up, as a given amount of years has less effect on our perceived aging, perceived sense of going through time. And then another example might be with Moore's law. So if the number of transistors you've already got on a chip is, say, 2, that's how many you currently know how to get on a chip, onto a chip, then adding 1 to go to 3, so adding an extra transistor, if you so far know how to put 2 on a chip, that's kind of a big deal. You know how to do 2, to squeeze an extra 1 on is quite a big deal. But if you've already got 1 million transistors on a chip, going to add an extra 1, squeeze an extra 1 in, it's not a big deal at all, kind of easy. So it would be adding, hundreds of thousands. That would be a big deal if you've got 1 million on there. So we can see that it's a similar thing, that it is the logarithm that matters. It's the perceived difficulty is proportional to the logarithm, like a Weber-Fechner law. So we might say that it's the perceived difficulty, the increase in difficulty, is proportional to the relative increase in the number. And that is a Weber-Fechner law, and that is why we are getting this exponential Moore's law for the rate of growth of the number of transistors on chips. So, as I say, a Weber-Fechner law is a very useful thing to think about when you're seeing an exponential relationship. You can start to sort of drill down and see, well, what must be the way these variables behave that causes this exponential law? And now let's have a look again at y equals log x and ask, what is dy by dx? So we've seen y equals e to the x, and we know that dy by dx equals e to the x, which equals y. What if y equals log x? What's dy by dx? Well, if y equals log x, that means that x equals e to the y. That's the definition of the logarithm. So we can find quite easily dx by dy, that is just equal to e to the y, which is equal to x. And then all we need to do now is flip it, because we learned that these derivatives do behave like fractions. So we can flip dx by dy to dy by dx and flip the other side, take the reciprocal in other words, becomes 1 over x. So when y is log x, the derivative is 1 over x. And conversely, if we see an equation dy by dx equals 1 over x, then we know that y equals log x. And I mentioned that the a in something like y equals a e to the kx is kind of like a constant of integration. And with knowing this now, we can perhaps see exactly what that means. So let's have a look at that. So let's suppose we have the equation dy by dx equals ky. Remember, this is going to give us an exponential solution. We know that the equation that obeys that is y equals ae to the kx. And to solve this, we can rearrange a bit. We can multiply through by 1 over y, and we can also multiply through by dx. So we'll end up with 1 over y dy equals k dx. And then we can integrate this. And 1 over y, to integrate that with respect to dy, we want to take the anti-derivative of 1 over y. Well, we've just seen that. It was log y. That's what we just worked out. And we also need to take the antiderivative of k. Well, that's kx plus c. We saw in the last lecture. If you differentiate that, you'll end up with k.
In other words, c is the constant of integration.
So we've got log y equals kx plus c. And we can then take the exponential of each side, we could say. So it's e to the log of y. Well, e to the log of y is just y. Remember, e to the power of and log are inverses of each other. So y equals, and here we've got e to the kx plus c. And that can be written as e to the kx times e to the c. And c is just a constant. So that can be written as a, another constant. And so that equals a e to the kx. And what we can see here then is that this constant of integration, c, becomes transformed by e to the c into this a that comes in front of the ae to the kx. So that is why I said that a kind of is a constant of integration. And as we know, that if we've got indefinite integrals like this and we don't have initial conditions, we have to take into account that there is this constant of integration that we may not know what it is. But then if we're told the initial value, we can then work out this constant of integration, and we've already seen that a is related to the initial value. It is y0. That is y when x equals 0. And again, this is useful to know because when we're solving some equations that we will meet in the theories we're going to be dealing with, we sometimes have to do this, move these y's around to see and to solve the equation. Now finally, I want to talk about a trick that's used often by economists for dealing with equations, and that is also going to be useful for us in some of the things we will consider. But before talking about this trick, it would be we need to cover a couple of other points so that we can understand how it works. So the first thing is the derivative of a product. So supposing we have y equals u times v, where u and v are both functions of x. Then if we want to find dy by dx, the rule is that it is equal to u times dv by dx plus v times du by dx. That is known as the product rule for differentiation. And I can show you where it comes from. So if this is a rectangle with side u there and side v there, and y then is the product of u and v, so it's the area of this rectangle. If we increase u by an amount du and v by an amount dv, we've got a new rectangle, and this area around that rectangle, that's the increase in y. Y has gone from here to this larger rectangle. So the area of around the edge here is dy, this whole thing around the edge here. So, but this part is du times v. That's the area of that rectangle, du times v. And the area of this one is u times dv. Yes, it would have been better if I put that the other way around. And then this is du times dv. So we have from here that dy equals, let's say, u dv plus v du plus du times dv. And then we divide through by dx. So there. And everything is fine except over here we've got, let's say, du by dx, that's fine, but it's multiplied by dv. And this is an infinitesimal, so it's 0. So 0 times whatever this is 0. So we can cancel that. So that is our product rule that we started off here. So that's one thing to note. And the second thing, preliminary, is that we know that d by dx of log x equals 1 over x. It's one of the things we just derived earlier. So we can then put the dx up on the other side and write that. The differential of log x is equal to the percentage change or fractional change in x. The change in log x is the fractional change in x. So for example, in our Weber-Fechner law, we had ds over s is proportional to dz. And we could have written that as d of log s is proportional to dz, which kind of makes sense because we found that z is proportional to log s. So yes, so ds over s is the same as d of log s. And d of log x is dx over x. So the differential of the logarithm is equal to the fractional change. So now let's look at this technique. So supposing we have an equation like this, x equals y times z squared. And we're interested in the rate of change of x. So we're interested in dx by dt, rate of change over time. Well, to work that out, we're going to have to use firstly our product rule, which means that we'll have z squared times dy by dt. If you remember, perhaps I should write it up, d by dt, let's say, of uv is going to be equal to u dv by dt plus v du by dt. So that's what I've done here. If this is v, I put v du by dt, and then we've got to have u dv by dt, so that's y times. Now to differentiate z squared with respect to time, we have to use our chain rule. We're differentiating this with respect to time. D by dt of z squared is equal to d by dz of z squared times dz by dt. And d by dz of z squared, we should definitely know, is 2z. So d by dt of z squared is 2z dz by dt. So let's put the 2 there, 2y z dz by dt. And this is pretty horrible. If I'm trying to work out how x is changing, I've got z squareds and dy by dt, and it's very difficult to see what's going on. And what we're going to look at is a way we can transform this equation to make it a lot easier to understand what's going on. So what we'll do is we will initially take the logarithms here. So we get log x is equal to log y plus the logarithm of z squared, which is 2 times the logarithm of z. We can see that because we've already seen that when you multiply, you add when you take the logarithms. So z squared is going to be z times z. So when we take the logarithm, it'll be log of z plus log of z. So it's 2 log z. But really the more general formula of log of x to the n is equal to n log x, which we could prove using our rules of exponents. But yes, so we're using that there. So we've now got log x equals log y plus 2 log z. And we can now differentiate. We'll get d of log x by dt equals d of log y by dt plus 2 times d of log z by dt. And we may now remember the thing that we just showed, that d of log, let's say u here, is equal to du by du over u, is the fractional or percentage change in u. So this is the fractional rate of change in x. It's a fractional change in x over the time taken. So it's it would be something like 10% per year. So the fractional change in x is 10%, and it's the rate with respect to time, so it's per year. So we might have the situation where we're told that z is increasing at 2% per annum, and y is increasing at 3% per annum. And then we know from this equation that x is increasing at d log y by dt is the the percentage rate of change in y, so that's 3% per annum, and z is 2%, but it's plus 2 times 2% per annum, and so 3 plus 2 times 2 is 4. So x will be increasing at 7% per annum. So working with these logarithms and thinking in terms of relative changes, this equation becomes a lot simpler to see what's going on. We just that the percentage change in x is a simple sum of the percentage changes in y and z, and we don't have a formula that mixes up y's and z's. And you can imagine that in economics this is a kind of thing that often occurs. Economic models are going to say that it depends on, something like the tax rate and the rate of inflation, and there are going to be some equations that depend on those things, and tax rates and rates of inflation will be measured in terms of percentages. So it's quite easy to, if you put the equations in this form, to work with the percentages rather than the absolute values of the variables that you're considering. And I'll just mention a little bit more notation here. We could write this as dx by dt plus dy equals dy by dt plus 2 dz by dt, where x equals log of x. So I've used a little x to represent log of x, and similarly for y and for z. That's a 2. So little y is log of y, little z is log of z. So that's just a matter of notation, but that's something we may use when we're dealing with equations that we manipulate in this way, that instead of writing out log x, we'll use the convention that the capital is the absolute value, and the x is the value, and little x is the log of the value. And we also saw then that if d of log of u equals du over u, we could write that then d of log u by dt is equal to 1 over u du by dt. We put the 1 over u in front, then we've got the du over dt. So this equation could also be written as 1 over x dx by dt equals 1 over y dy by dt plus 1 over z times 2 dz by dt. Or probably better to put it the other way around. 2 times 1 over z dz by dt. So it's just putting 1 over the variable in front of the dy by dt. So that and that are all kind of equivalent ways of writing the same thing, where we assume that we use the lowercase to represent the logarithm. So, as I say, that's a useful trick that we will be drawing on later in the course.